Hi guys, Mr. John here. In this video we're going to be looking at how to draw Lewis structures for relatively simple compounds. So we're not going to be talking about anything that breaks the octet rule, and we're not going to be talking about resonance structures. The first example I want to go through is HBr. Now you should have a list of rules for drawing Lewis structures in your notes. You should be referring to those rules as we go through. Step one, anytime you're drawing a Lewis structure, is to sum up the valence electrons for all of the atoms. So in this case, HBr has 1 valence electron. Bromine has 7 valence electrons, which is going to give us a total of 8. Step number 2 says arrange the symbols with single bonds between them. So we put H single bond Br. Step number 3 says complete the octets of all of the outside atoms. Well, in this case, hydrogen cannot have an octet, and bromine is going to be considered our outside atom, so we're going to give that an octet. Step 4 says to count the electrons on the structure, so let's count them up. We've got one lone pair there, that's 2, 4, 6, and then there's 2 in the bond here. That gives us 8, which means that bromine has an octet. Hydrogen doesn't need an octet because it only gets 2 valence electrons, and so we have the right number of electrons, 8, and everything has an octet, which means we're finished. For PCl3, we're going to go through the same process. First, we count the valence electrons. Phosphorus has 5. And then we have 3 chlorines. Each one has 7. So that's going to give us a total of 26 valence electrons that we have to account for. We put phosphorus in the middle. We single bond all of our chlorines. And then we give all of our outside atoms an octet. So let's count up valence electrons now. Each chlorine has its full octet, and there's 3 of them, so that's 24 electrons, which means we still have 2 electrons that are unaccounted for. And the rules say that if we have extra electrons, we put them on the central atom, right there on the phosphorus as a lone pair. And just a side note, it doesn't matter where you put the chlorines, left, right, top, bottom. As long as there are 3 single bonded chlorines, you're good to go. Lewis structures are not 3D representations, they're 2D representations, and so there are limitations. As long as the bonding is correct, it doesn't matter where you put things. But now we have 26 electrons. Phosphorus has an octet, so it's happy. All of the chlorines have an octet, and so this structure is finished. The next example is CH2Cl2. So let's count up our valence electrons. Carbon has 4. We've got 2 hydrogens with 1 valence electron each, and 2 chlorines with 7 valence electrons each. And so that's going to give us a total of 20 valence electrons that we have to account for. Sometimes it gets a little bit tricky to tell which element, which atom is going to be in the center. In this case, it's carbon. You usually go with the least electronegative, and if carbon's involved, it's almost always in the center. So I'm going to put my hydrogens on the top and bottom. Again, it doesn't matter where you put them. You can put them left, right. You can put one top and one right. It doesn't make a difference, as long as you have all of the bonds that you need. Let's give everything on the outside a full octet. Hydrogen already has its duet, so it's okay. Let's count up all of the valence electrons. Chlorine's got 8 over here, 16 over here, and then 18 and 20. So we have all of our valence electrons that we need, and everything has an octet, which means that this structure is A-OK, and we can move on. The next example, HCN, is the first one where we're going to have to make multiple bonds. But we're going to start the same way by adding up the valence electrons. Hydrogen has 1. Four for carbon, 5 for nitrogen. That gives us a total of 10 electrons that we have to account for. So carbon, as I said before, is almost always going to go in the middle. We'll single bond it to nitrogen and to hydrogen. And then we'll give the outside atoms their full octet, or duet in the case of hydrogen. And let's count up the valence electrons. We've got 2 here and 8 here, so that is a total of 10. So we have all the valence electrons that we need. The problem is carbon does not have an octet. And so the way we're going to give carbon an octet is we're going to take lone pairs off of the outer atoms, in this case nitrogen, and we're going to move them into the area between carbon and nitrogen and make a bond. In this case, a triple bond. And so what we end up with is carbon triple bonded to nitrogen. Nitrogen still has 1 lone pair, and hydrogen over on the other side. So now we have the right number of electrons, 10, and everything has an octet. So we've satisfied those rules. Okay, NO plus is a polyatomic ion, so we have one special rule for those, which is going to come at the end. But we're going to start it the same way, counting up the valence electrons. Nitrogen has 5, oxygen has 6, and then we need to subtract 1 because NO plus means it lost a valence electron. That's how it gained that positive 1 charge. And so we have a total of 10 valence electrons that we need to account for. Let's connect these with a single bond. And then we're supposed to choose a central element. There isn't really a central atom in this case, so let's just pick the one that is the least electronegative, which is nitrogen. We'll call that our central atom. So we'll complete the octet on our outside atom, which is oxygen. That has 8 valence electrons. We need 10, and so we put the remaining 2 in a lone pair on the central atom. Oxygen has an octet, but nitrogen does not, and so we're going to do the same thing we did last time. We're going to take 2 pairs, and we're going to move them to the middle to make a triple bond. So nitrogen is triple bonded to oxygen. Each one has a lone pair. You can put those on the top of the atom, on the side, on the bottom, it doesn't really matter. And then the last step is every time you have a polyatomic ion, you put the whole thing in big square brackets, and you put the charge of the ion outside on the upper right. Okay, the last example is C2H4. So let's count up our valence electrons. We've got 2 carbons with 4 electrons each, 4 hydrogens with 1 electron each. That gives us a total of 12 electrons. So carbon goes in the middle. In this case we have 2 carbons, so we're going to put them both in the middle. And then we'll just kind of distribute the hydrogens around symmetrically like this. I put the hydrogens at an angle just because from experience I know that's how they're going to end up. But it doesn't matter, they can be straight up and down. Okay, so this has 1, 2, 3, 4, 5 bonds, so that's going to give us 10 electrons. We still have 2 more, so we got to put those 2 remaining electrons on the central atom. Well, we have 2 central atoms here, so let's just pick one. We'll put them here on the left, doesn't matter. So all of the hydrogens have their duets. The carbon on the left has an octet, but the carbon on the right does not. And so what we're going to do is we're going to take this lone pair and we're going to move it in between the 2 carbons to make a double bond. And so now we have carbon double bonded to carbon. We put our hydrogens here. And there's our final structure.